What's going on, guys? Today we're doing LeetCode problem 230, kth smallest element in a BST. This is a medium problem. Given the root of a binary search tree and an integer k, return the kth smallest value, one index, of all the values of the nodes in the tree. Okay, so first things first, we got to make sure we understand the problem. So we have the root of a binary search tree, and we have some integer k. So we need to return the kth smallest value. So if they give me 1, that is, I need to return the first smallest value in the tree. So in this case, that's 1. If they give me 3, I need to return the third smallest value. So 1 is the most small, then 2, then 3. So 3 is the third smallest value, so the output is 3. So when you first see this problem, I think one natural intuition you might have is, okay, well, if I can find some way to iterate through all of the nodes in the tree, as I hit each node, I can store its value in an array. And then once I have my array, I can separately just sort the array, and then once it's sorted in ascending order, I can easily find the kth smallest value. And that's not a bad strategy. That can definitely work. But sorting takes time complexity of n log n, because that's what merge sort is, n log n. And we can actually do it a little bit faster than that if we utilize a property of binary search trees. So the trick to this problem is knowing how binary search trees are structured. And the way that a proper binary search tree is structured is that we have a root node, and then every node in the left subtree of that root has to be smaller than this root node. Similarly, every node in the right subtree has to be greater than the root node. And this is consistent not just with this initial root, but when 3 is the root, the same thing applies. So this 2 and this 1 have to be, their values have to be smaller than 3, and then of course this 4 has to be greater than the 3, okay? So if you know this to be the case, then you can sort of intuitively, I think, understand that, okay, well, the very smallest value is going to be all the way to the bottom left. So it's that 1. And then the next thing you can realize is that if we traverse through this tree, just going gradually, basically moving to the right through the tree, we're just going to be going in order. Well, and so what you find is that you want to do an in-order traversal of the tree. So there's for doing a depth first search, you can do a pre-order, an in-order, and a post-order to go through the tree. And really quick, just want to iterate or explain what those are. So if you already know, then you can fast forward a little bit, but I'm going to explain. Pre-order, we have the root, followed by the left subtree, followed by the right subtree. Okay. In order is left subtree, root, and right subtree. And then post order is left subtree, left, I'll just say left, right subtree, and then root is last. So notice how root is the only thing that's really changing here. It's always left then right, but root can either be at the start, the middle, or at the end. And if root is in the middle, then that's in order, meaning we're going to go from the smallest all the way through the highest values. So it's worth knowing these 3 things. If you don't, and I would encourage you, if you're not comfortable with this, there's actually a really great video that I found that explains intuitively how these make sense. I'll link it in the description. But yeah, with that said, we would like to do an in-order traversal. So let's get started with that. And so actually something else I want to do is I want to make a separate method for the in-order traversal. And as I go, I'll try to explain why I'm doing that. But for right now, just go with it, I guess. Okay. And we're going to be doing a recursive in order traversal because I find the recursive, for depth first search, the recursive solutions are really pretty straightforward and simple. Well, not straightforward, but they're clean, at least. They can be a little mind-boggling. Okay, so for the in-order traversal, what do we want to do? Well, first of all, we don't need to return anything here. We still need the root. We don't actually need k for this in order traversal either. Oh, okay. I remember exactly why I made a separate function here. It's because I want to make the separate function because in this, I basically just want to return like whatever the answer is. It's not going to be this, but I just want to have a simple function that returns the answer. So inside my function, I want to call the function that finds the answer, and then I just want to return it. I don't want to have to deal with returning the answer inside of the recursion because it'll be a little bit messy in my opinion. So with that said, what are we going to do? We're going to, well, basically we want to do this recursive in order traversal, and we want to store the array as we go through the in order traversal. So I'm going to make an empty array here. And then I'm going to call self.inOrder traversal. And that's going to be on root. And I'm also going to pass in the array, which means I'm going to have to add it as an argument here. So list of ints. Awesome. Okay. So now how do we do the in-order traversal? Well, first things first is we want to establish it's recursive and we need a base case. So I'll say if not root and return. Just exit out of our function. So I want to call in order traversal on root dot left. Oh, I I knew I messed something up here. I can't just say this. I have to actually give it a name. So I'll just call it I'll label it clearly. I'll be very verbose about it so it's clear what's happening. So in order array, which is this array. Just for abundant clarity, we'll rename all these to in order array. So what do we want to do? Well, we want to add items to this array in order. So let's just break down what's going to happen when we call in order traversal on root.left. So first of all, we're starting with just the root, okay? So that's right here. Look at this 5. We say if not root return, but spoiler alert, we're not hitting that. So then we call in order traversal root.left. So now we're on to the 3. And then same thing, we're not hitting the if not root. So we're down here. And now we're down here. And now what happens when we hit the child of this? Well, we hit this if not root, so we return. So now we're back at this quote-unquote level of the recursion right here for this 1. So what do we want to do now that we're actually inside of that? Well, now we want to append that number to the array. So we want to say in order array dot append root, which is the root that we're on, root dot val. So the last thing that we're missing is the traversal for the root dot left, or the root dot right. So we're starting at the 5, we're going here, we're going here, we're going here. We're checking the left child. There is no left child, so we're returning. and now we've appended this 1. And now after we've appended this 1, we call in-order traversal on the root.right. But that's also none. That doesn't exist, so we just return. So now the recursive stack, quote unquote, is going back up to the 2. And so we're calling this line append the 2, and then again in-order traversal on the root.right, but that's just non-existent, so we just return. Okay, so now the recursive stack is tracing back to the 3, and we're appending the 3 to our array. And then see, now that we've appended this one, we're looking for anything that could be, slightly greater than it. And this is the thing, it's going to be slightly greater, but it's not going to be greater than this, because that's how binary trees are structured. This entire subtree has to be smaller than this 5. So that's why the 4 is the next highest value. So so we're doing in-order traversal on root.right, which is the 4. That means we're going back through this function. We're not hitting this. We're calling it on root.left, but that's just going to return. And then we're appending the 4, and then we're calling it on root.right, which returns. And now the recursive stack just finished doing what it needed to do for this 3. So now it's going to this 5, okay? And actually on that 5, we just finished our entire traversal for root.left, which was the 3. So now we're hitting in-order array.append, and we're appending the 5. And then finally, we're calling in-order traversal on root.right, which is this. We're appending this 6, and then, but I shouldn't say we append it yet. So we call in-order traversal on the 6. It's not the root. We call in-order traversal on the left child of the 6, which is non-existent, so it returns. So then we call append the 6 value, and we call in-order traversal on root.right, which is non-existent, so it returns. And so now we've just gone through our entire binary search tree, and we have made a list of all the elements of it in order, and it's O of n because we just went through it. We just went through each node, and we only iterated once. Yeah, so that's our in-order traversal. So the cool thing is that we call the in-order traversal, and we're literally passing in this in-order array. So all the changes that we're making to the in-order array are actually affecting this in-order array. It's not like different, if that makes sense. You're actually changing the values in this. So what do we need to do now? We have our array in order, and we need to return in order array, and we want to return, well, we know the first element is the smallest, right? And then the last element is the largest. So the kth smallest element is just the kth element, except for the fact that we have to remember that it's 1 indexed. It wants me to return the kth smallest value, and let's say k is 1. So it wants the first smallest value. If I return in order array of 1, then I'm actually returning, the second smallest value, because arrays start with an index of 0. But if I do k minus 1, 1 minus 1, then I'm returning in order array of index 0, which is the actual smallest element. And so as you can see, this is what we want to return. So with that said, let's run it and see how it goes. Runtime error, classic. So very important, very important. Got to put self. I could copy and paste, but I think it's faster just to type it real quick. All right, let's run it again. Runtime error. Oh, and another thing, in-order traversal requires this in-order array as an argument. So foolish me, thinking that I don't need to pass it in every time. Be better than me. Don't make these mistakes, or do and learn from them, which is what I should do. Just make sure your parameters match the functions you call, and use self. Let's run it again. And it's a runtime error. Oh, because this is just oops. This one doesn't need it. This is just root.val. This is just appending to the array. So let's run it again. It's good to be able to figure out your errors. Solution object has no attribute in order array. Oh, again, it's not self because it's a parameter. Sorry. We only need self when we're calling the function, which I knew I just didn't notice. Yay, accepted on the test cases. Let's submit it. And cool. Now you'll see it beats 39%, which might not seem good, but if I submit it again, it should be different because it's pretty random. Now it beats 70%. We are killing it. We're crushing it. So that's a lot of nonsense, but hopefully this explanation made sense. Thank you so much for watching.